Hey everyone, I'm Nick, and in this episode of CUDA Crash Course, we're going to be talking about how we can kind of simplify our code for that 1D convolution and still use shared memory. So a lot of times there's this trade-off between simplicity and performance. So if we have very simple code, it often doesn't perform terribly well, and if we have really complex code, it's often very difficult to understand and kind of prone to things like bugs. Just based upon having to keep track of things like synchronization, when values are valid in, say, shared memory, making sure that your indexing is correct when you're going between loading things from, say, a global array or using it from a local shared memory array. And so we're going to talk about that in context of this 1D convolution again. So we'll go ahead and use that as a case study and to kind of just refresh what the kind of idea was here with our shared memory implementation that we looked at last time. Was that we would have, some array that we're going to do a 1D convolution of, and this would have some values in it. Let's say 1, 2, 3, 4, 5, 6, right? And we also knew that, with something like this, every single thread block that we launched was going to have some halo elements. So, every single thread would have some halo elements, and then the array itself would have some halo elements. And so in this case, we'll just consider that we just have a small array, and that our only halo elements are, to the left and right of the array, and we're only launching a single thread block just for simplicity. So what we kind of saw was that, we'd still have elements out here that we needed, and let's, because these are outside of what's actually valid data for our convolution, but we need them to calculate these edge values for the convolution, we still need to include them. And so what we did in our initial implementation was we'd launch as many threads as we had elements in the kind of the primary array. So in this case, it'd be 6 threads. And we'd say, okay, every single thread will load in one element based upon its position. So we kind of shifted everything to the left just to kind of help out with things like warp divergence. And then some elements later on would have to load 2 elements, right? So they'd load a second element in. And so we still have 6 threads launched, but what we kind of did with an if statement was say, okay, these are out of bounds. They're not going to load anything. So only a subset of the threads were going to load something new on the second round of loads into shared memory. Okay. So this led to some kind of complex code where we had A, 2 sets of loads, and B, we had to keep track of a lot of slightly more complicated indexing. Now, you might be wondering, well, how do we make this a little more clean, but maybe still use shared memory? Well, one way to do that is by just saying, I don't really care if some of the elements have to be loaded from DRAM, because you have to remember that there still is a cache in the system. So being a data cache. So because I have an L1 cache and an L2 cache, not every single one of those accesses most of the time will be a miss. And if my working set is a reasonable size, there's actually a good chance that I might be hitting on things in the L1 cache, and I don't really have to worry about the fact that not every single element is in shared memory, because in architectures that have unified L1 and shared memory cache, accessing L1 versus accessing shared memory is going to be relatively comparable. So what we can end up doing is say, all right, well, if I want to access, the 6 elements that I load initially, into shared memory, okay, those will be in shared memory, of course. However, for these upper 4 elements, I'm not even going to bother doing any kind of index calculations. All I'm going to do is say, if you want these elements, you have to, go ahead and use that green again. These have to go all the way out to whatever that, primary structure is. So, first it'll be the L1 cache, then, to the L2 cache, and then hopefully not, out here to DRAM. All right. So, we generally don't want that. So we don't want to be going all the way to DRAM, but like as we kind of said earlier, there's some locality here. So odds are it's going to be some unlucky couple of threads will load these values from DRAM, and then it'll get stuck in the L1 cache, and then other people will end up hitting on it in the L1 cache. So let's go ahead and kind of refresh ourselves with what the shared memory implementation looks like. to kind of motivate why we would sacrifice some performance in the sake of programmability. So let's go to 1D tiled, and let's look at convolution.cu. So let's see, just from the case of inside the code itself. So what do we have to do? So we calculated some things like global offsets and another offset for the second set of loads that we need to do. And then we do a first load where we just based it on the thread ID for the particular thread block. And then we'd have an if statement that would check to see if the offset after we do this add up here is less than the number of padded elements, making sure that those last couple of threads don't load in elements that we don't really care about. And then what we do is we'll go ahead and load whatever those elements are based upon the offset inside of shared memory, and then the global offset within that global array, right? And then down here we just have the very simple, and everything's in shared memory, so we can just kind of have a simple loop and not have any conditional statements in here. But as you can see up here, we've got to keep track of a lot of kind of I wouldn't say non-intuitive indexing, but more complex indexing than we would like. And if we can get reasonable performance without having to do this, and maybe we're not on some latency critical task, sometimes we want code that's more maintainable. So we'd want that first and foremost sometimes. So let's go ahead and see how, just kind of review how fast this one went. So as we can see, this ran, and we'll run it a couple times. It looks like that convolution 1D runs in about 94 microseconds. Now you have to keep in mind that this performance will differ depending on what architecture you're running on, and also my numbers are going to be slightly biased because I'm running graphics on the same GPU as I'm running compute, and so that always leads to inaccuracies when it comes to profiling. Ideally, you'd want a completely separate GPU, not running any graphics at the same time, because there's going to be some contention for resources. Okay, so we'll go ahead and go to our new implementation, which we'll call 1D cache, and we'll go ahead and open this one up. Right, so how do things change? Now down here in the actual main function itself, nothing's really going to change. We're just going to allocate some memory and copy it over, and we're still going to be using constant memory for the mask, because the mask still isn't changing. So if we go up to convolution 1D now, we see that it's a much narrower kernel. Now granted, a lot of the length of the other kernel stems from the fact that we've got all those comments, but as you can see, it looks fairly simple, and it stems from the fact that we really just have this single load. So what we'll end up doing is we'll just do that load of those lower, in the case of our drawn example, we're just going to do the load of these lower 6 elements, and then these unlucky elements at the top, we'll just load them from DRAM, and hopefully we'll hit on them in the L1 cache. So, here we go. And here, all we need to do that is we just check to see if our thread ID plus whatever j is, so j being what we're iterating over at the mask length, we just check to see if it's greater than the block dimension. If it's greater than the block dimension, basically what we've done already is that when we're allocated shared memory, we're just allocating enough shared memory so that every single thread loads one element. So if we're past the 256, elements 0 through 255 will be in shared memory, but all the elements after that, which will be those upper elements right here of the main array, and then the halo elements up here, those won't be in shared memory, so we'll have to go out to DRAM for them. So in those cases, all we need to do is check to see if whatever this offset is of the thread ID plus j is greater than the block dimension, and then we'll just go ahead and add to temp whatever is in array being that pointer that we passed in as an argument, being what's in global global memory or in DRAM of the GPU, and we'll just multiply it, but whatever's in constant memory by that mask, right? And then so here, otherwise, if it's not greater than, we'll go ahead and just load it from shared memory. So here, all we need to do is access sArray, which is what we have allocated up here as this shared memory that's dynamically allocated. Remember, this extern says that we're going to pass in the amount of shared memory as a parameter. And we'll go ahead and use shared memory for all of those cases. So let's go ahead and see how this runs. and then likewise, we just write back the results. But as you can see, it really greatly simplifies how we can reason about this program. We just have a single load into shared memory, and then we just have a very simple balance check. If it's outside of those 256 elements in shared memory, all we do is get it whatever the value should be from DRAM. Okay, DRAM or the caches, hopefully the caches. So we'll go ahead and compile this using NVCC. First, we'll just run it to make sure it runs correctly. Okay, so it passes our functional test. So just as a reminder, our functional test, it does it on the CPU side, it does convolution, and then we just have an assert statement that checks the result that we copy back with whatever we calculate here in our CPU side calculation. And then we can go ahead and do a oops, we have to run it, so we have to do dot slash. We can go ahead and check to see what the performance is like running it. And as you can see, it's 104 microseconds. So if we go ahead and go back to the previous example, so if we go to the 1D tiled version, and we go ahead and run this one as well, we see that 93 microseconds versus 104 microseconds. So we sacrifice some on performance, but in reality, this isn't a terribly big gap. It's nowhere near as big as the gap that we saw between just the tiled version, or rather, it's nowhere near as big of a gap as the naive version versus the constant memory version, where it was something like a 2x speed up that we saw. So sometimes, just for programmability and usability, we can cut corners sometimes with the performance optimizations depending on our needs. Sometimes we can say this is good enough. Everything doesn't need to be optimized to its fullest. You don't need to worry about optimizing your Hello World program. So we can get away with things like that. So that's going to go ahead and do it for this video. This is just kind of the final, I wouldn't say the final alternative, but it'll be the final alternative to an implementation of 1D convolution that we're going to cover in terms of programmability versus performance. As always, feel free to check out all the code that I post on GitHub. So here's the GitHub page. It's got all my other courses on things like C++ and parallel programming in C++, as well as some things on object-oriented design patterns, and there'll be some stuff on systems programming as well. So if you go to the CUDA programming section, that's where I keep all this code that we've been looking at. Kind of broke it down by the sections, so whether or not it's vector addition using unified memory versus just kind of the hello world of GPU programming, which is normal vector addition, optimizations to matrix multiplication using CUDA libraries, and we're on the convolution section. So you feel free to check out the videos are linked on the left, the files on the right. And so if we go ahead and go to convolution and we look at 1D tiled, or actually 1D cache, this is that example that we looked at today. So feel free to download this, play around with it, perform some optimizations on your own. And of course, let me know if you have any questions. But I'm Nick from Coffee Before Arch, and I hope you have a nice day.